In this video, we're going to continue our discussion of concavity and curve sketching. We're actually going to work through an example, and this example is going to be using a polynomial function. Let's take the function y equals x cubed plus 6x squared plus 9x plus 2 and look at what we've used so far for curve sketching to come up with a graph. So we're going to use both the first derivative test that we've talked about previously, and we're going to use the second derivative test, which we're discussing in this lesson. So let's start by taking our first derivative. So we know that the derivative of y would be y prime, and that would be 3x squared plus 12x plus 9. Now remember that we want to find our critical points, so we're going to set that equal to 0. Notice that all of our constants are divisible by 3, so let's factor out a 3. And then let's look at our quadratic and see that it also factors to x plus 3, x plus 1. So now if I set that equal to 0, remember that we know that if we have three things being multiplied together and getting 0, at least one of those is 0. Well, 3 can't be 0 because it's a constant. So what would happen if I wanted to make x plus 3 equal 0? The next would be negative 3. And if x plus 1 was equal to 0, the next would be negative 1. So we'll go ahead and make our sign chart using our critical points of negative 3 and negative 1. So let's pick some values that are on either side of that, or during those intervals. So to the left of negative 3, let's do negative 4. I'm going to go right into this factored form and see what happens. So if I put in negative 4, 3 is positive. Negative 4 plus 3 would be negative, and negative 4 plus 1 would be negative. So I have a positive times a negative times a negative. That's positive. I'm going to substitute in negative 2 for the interval between negative 3 and negative 1. So then I have 3 is positive, negative 2 plus 3 is positive, and negative 2 plus 1 is negative. So a positive times a negative would be negative. And then to the left or to the right of negative 1, I'm going to use 0. So 3 would be positive, 0 plus 3 is positive, and 0 plus 1 is positive. So that all turns out to be positive. So we are increasing, decreasing, increasing, and that's what our graph of y will resemble. Because this is a polynomial, I can kind of sketch in what I think y will look like. So let's go ahead and write our intervals of increasing and decreasing. So we are increasing from negative infinity to negative 3 union, because we've got two parts. Let's move that down. And then we're also increasing from negative 1 to infinity. And then we are decreasing from negative 3 to negative 1. Now we also have some relative extrema, so let's list those. We have a relative max at negative 3. Then if I go back and put negative 3 into this equation, you're going to find that you will get positive 2. So our relative max would be negative 3, positive 2. Then we also have a relative min right here at negative 1. And again, if I put negative 1 into that original equation, then I'm going to find out that my y value is negative 2. So I do have some points now to sketch when I graph this. So this is what we have so far. We have our y and our y prime. Now we're going to go to the new material, and we're going to look at the second derivative test. So I'm going to go ahead and take my second derivative. And when I do, I'm going to get 6x plus 12. But just like before, I want to find what would make that equal to 0. Now critical points are technically only from the first derivative. So when I substitute or set this equation equal to 0, I do get that x is negative 2. So that's the value that I'm going to put on my second derivative sign chart. So just as before, I'm going to pick numbers on either side of negative 2. So let's use negative 3 and negative 1. And we'll substitute those back into my derivative. So whatever derivative I'm working with is where you want to substitute in to fill in your signs. So if I put negative 3 into my second derivative, I'm going to get a negative, because I have 6 times negative 3 plus 12 would be negative. If I put in -1, I'm going to get a positive. Now I have my concavity. We know that a function is concave up when the second derivative is positive, and it's concave down when a second derivative is negative. So now we can write when we're concave up and concave down. So looking at my sign chart, I'm concave up from -2 to infinity, and I'm concave down from -infinity to -2. Now the next thing I want to do when I look at my second derivative test is look for a point of inflection. Remember from our definition, we said that points of inflection are points where the derivative is equal to 0, the second derivative is equal to 0, and you have a sign change. And if you notice, -2 meets that criteria. That's the point where the second derivative is 0, and to the left of the value -2, I have that the sign is negative, and then it changes to positive. So I do have a point of inflection of -2. Then to get the y value, I'm going to substitute that back into my original equation. You always get y's from your original equation. And when I put that into my original equation, I get 0. Now the last thing that I want to do is take everything we've done up to this point and go ahead and combine it into one graph. So I went ahead and rewrote our sign charts and our relative maxes and mins. Now the first thing I would suggest you do is start by plotting your points that you have. So you have a relative max, a relative min, and a point of inflection, which are going to give you 3 ordered pairs. So if I go to -3, 2, plot a point there. Go to -1, -2, plot a point there, and then -2, 0, and plot a point there. Now I'm ready to just fill in the graph by looking at what's happening in my sign chart. So let's divide this up into some intervals. Let's first of all look at what happens as we approach the graph from the left of -3. So as I'm approaching towards -3, notice that my graph, and let's go ahead and draw this back in. My graph is increasing, but my concavity says I'm concave down till I get to -2. So I'm going to be increasing and concave down. Then when I get to -3, I start decreasing, but I haven't changed concavity until I get over to -2, so I'm decreasing concave down. Then at -2, I've changed concavity, but my graph is still decreasing till I get to -1. So I'm now decreasing concave up. At -1, I changed to increasing, but I'm still concave up. And notice that from -1 on, the graph continues to increase, and we're always concave up. So it would increase concave up, and that should be what your graph is going to look like. And you can check that with your graphing calculator. Notice that this is the same kind of work you were doing with your first derivative, except now you're going to be able to tell how your graph bends by looking at the concavity and then getting those points where your concavity changes, which allows us to have much more accurate graphs than we were previously able to do.